So I'm going to present a couple of examples on the PyFluent usage. The first one is the meshing with PyFluent, and the second is application of PyFluent solver to end-to-end machine workflow-driven approach. So the first one is here. What you see is meshing with PyFluent. It's used to mesh this heat exchanger. So we have a set of different objects here to be meshed using polyhedral cells. We have a PCB kind of body here in green. Then we have the heat exchanger where the fluid goes through. The fluid goes through. We have some fins there in the heat exchanger, and then we have two different bodies on the outlet. And the purpose of this is to show you how easy it is. In fact, also how easy it's to complement with self-created tools that you may be able to produce. In this case, I am using two APIs that I tune. In this case, well, this is this toolkit.meshing. That is a wrapper. It's a object that I built on top of the PyFluent API for meshing, and basically reproduces the watertight workflow. As you can see here, if you have worked with the watertight workflow manual, is reproducing the different activities and action points that we can produce with the watertight. So first, I am just defining the CAD file that I'm going to read and the mesh file that I'm going to export. I create the absolute paths that I'm going to use, and then I invoke that object, the meshing watertight workflow, where I pass the number of processors I'm going to use, and I define whether I'm going to use it in interactive mode. I am running in interactive mode because I want to see you see on the right side here, on the right hand side of the screen, the GUI popping up and performing the actions that I'm going to execute here. So I am starting the meshing, as you can see, just execute this line here, interactive true, and then it starts Fluent interactively. The next thing I'm going to do is perform the task import geometry here. So I'm calling that object import geometry, and I'm passing the file name that I want to read and the length unit that I need to read in. So once I execute that, you will see that the geometry is imported. So it imports the geometry there. Sorry, I skipped one. The next one is add local sizing. So in add local sizing, I am going to leave it as it is. I am not passing any argument, so it will just update with the full values. And then I'm generating the surface mesh. And for generating the surface mesh of the object, again, I am selecting the proximity to edges, and I'm providing the maximum and minimum sizes of the mesh. In this case, 0.4 and 1.1. And when I click on generate, it will generate the surface mesh, as you can see in a moment. So generating the surface mesh, and it completes. Once generated the surface mesh, I'm going to the next task, describe object, which I am wrapping in this describe geometry, where I'm saying, okay, this is a geometry that is fluid with regions and regions with not void. It does contain only fluid regions because I'm not modeling the solid part outside. I'm not meshing the solid part, and then I am executing the create regions, update regions options that I have encapsulated in these two objects here. Here with update boundaries and update regions. So that gets executed. As I get executed, they update the different objects. So I'm happy with these values. And then I go to add boundary layers. So I will add boundary layers here. As it says there, I'm selecting, I'm providing the zone selection list to which I want to add the boundary layers to my geometry. I am providing the area where I want to scope it to. In this case is to selected zones. These zones here, I will add a number of 5 layers to grow in the boundary layer, and I will use this smooth transition control to grow them. Once I have added the boundary layers, you will see when I execute that command, it adds the smooth transition boundary layer again, and Then I go into generate the volume mesh. So in generate the volume mesh, I enable the check self proximity option, which is and the advanced options, but we can provide any of the options that we have here. We can provide it at the higher level of this object. And then the volume fill, I'm telling it to fill it with polyxcore. Finally, I invoke the write mesh object, so it will write the mesh to the mesh file that I defined at the beginning, and then I exit the code. And then the result is to have a workable mesh that I can use for solving. So as you can see, it's extremely easy to use this sort of implementation to generate a fluid mesh. The second example is the one I was mentioning there, to create an end-to-end workflow. In this case, it's not doing meshing, it's only solving, but the idea of this workflow is focusing on this mixing elbow. This mixing elbow has an inflow here that is injecting fluid at prescribed velocity and temperature. And there is another flow, a secondary flow, a second inlet here that is injecting flow at another speed at a different temperature. And the idea is obviously to see what is the conditions that form outside the mixing elbow here. So the idea is to show the power of PyFluent and how it can couple with other Python libraries. In this case, I am defining the simulation in Fluent. For the inlet velocities, I think I can show it. I will skip it out. But for the inlet velocities, I am defining a set of different properties. So for the velocities, in this case, I want to see what is the average temperature at the outlet. So I'm prescribing an NumPy array to provide the different inlet velocities for the cold inlet, which is this one, and the hot inlet, which is this one, which have a prescribed different inlet temperatures. And the idea is, okay, if I have these two arrays of different velocities coming from here and here, I want to build a machine learning model so that after building these sort of simulations and training the model, I don't have to do any more simulation, and then I can just run this 0D model. So if I provide any temperature at the inlet, any temperature at the outlet, it will tell me exactly what is the average temperature at the outlet, right? I want to be able to get what is the average temperature at the outlet without having to rerun a 3D model, just using my machine learning. And for that, I'm going to use the supervised scikit-learn Python library for machine learning, and XGBoost to create and construct the 0D model. I'm loading here a series of libraries. Then I am defining the geometry I'm going to read in. I'm starting Fluent and running it in 4 cores, showing the UI as well. This is good practice to make sure that what I am implemented is being translated correctly into the session. I'm reading the case file. As you see here, I am then reading the case file. When I read the case, I retrieve the output back into this Jupyter notebook so I can see what's going on, if everything has been read properly. Then I define the manual DOEs and NumPy arrays. Like I said, these are the velocities from the cold inlet and the hot inlet. And I am defining this loop to create, well, the different velocity inlet to prescribe, to loop over all these design points and run them all. So basically what's going on here is I am defining the boundary conditions. So I'm looping over these arrays of velocities. And for each array, I'm setting the velocity inlet with its prescribed velocity magnitude. I am defining the hot inlet with its corresponding velocity magnitude. I'm initializing the solution, and then I'm iterating for 5 iterations here, just for the purpose of showing here. Then I am defining a report at the outlet as the average temperature, and I'm getting that one. I'm saving that output, and I'm storing it in an array that will be used to train the machine learning model. Once I have that information and it has run, I exit Fluent because I will no longer need the So here I exit Fluent. I exit Fluent because I will no longer need Fluent running. I will just use the data that I have collected from these report definitions to execute the machine learning model, right? That's a good thing of living in this Python environment, that I am using Fluent as an external library, but then I am continuing the work in the prescribed session outside of Fluent. Here I'm plotting the response surface that I obtained from my Fluent data. So you can see here for the different hot inlet and cold inlet, what is the corresponding temperature at the outlet. And we can have a first idea of what's going on and what is the response with those two parameters. Then I use the data to, so actually I can embed into the window that the response surface, so you can rotate, you can explore all directly within Jupyter Notebook. And once I have, I think it's okay. There's some outliers there, but I can live with that. I'm going to move on with this data and pass it to the machine learning algorithm. Then I can implement that in the regression library, provide that array of inputs and outputs, and it will create using scikit, it will create the model train. So I split the data into training and testing, 80-20 training and testing functionalities, and then I uses that to train the model. Once it's been trained, it outputs a workable model that I can invoke, and with that I can create my 0D model that I can use as a neural network to get the response. And then here's what you see. I'm matching the training data. Then when I compare the unseen data, there's some differences, but I'm not so, you see, 294, 296, we are not so bad in predicting the outliers. That's all from my side.